Hi guys, hope you are doing great. So in this video I'll be discussing about Turing machines. Let's dive into the video. Table of contents. I'll be covering each and everything over the course of time, right from the introduction to applications. What is a Turing machine? A Turing machine is an accepting device that accepts the languages, recursively enumerable set, generated by the type 0 grammars. It was invented in 1936 by Alan Turing. It is a mathematical model which consists of infinite length tape divided into cells on which input is given. It consists of a head that reads the input tape. A state register stores the state of the Turing machine. After reading an input symbol, it is replaced with another symbol. Its internal state is changed and it moves from one cell to the right or left. If the Turing machine reaches the final state, the input string is accepted, otherwise it is rejected. Moves. At each step, the Turing machine writes the symbol to the tape under the tape head, changes the state, and after finally it moves the tape head to the left or right. Also, there is an exception in the Turing machine, that is, it can't accept an epsilon or lambda. Also, in almost all cases, n will be greater than or equal to 1, but never would be equal to 0. How does a human compute? Basically, we will write the input on a paper and then do the computation, that is, think and write the intermediate results on the paper. And finally, we will write output on the paper. How did Turing formalize human computation? These are some of the comparisons between human computation and machine computation. Turing is named after Alan Matheson Turing. Here the machine indicates the computing machine and the tape is compared with the paper where we write, and the tape head is compared with the writing on the paper. Formal definition. A Turing machine can be formally described as 7-tuple, where Q is the set of states, X is the tape alphabet, epsilon is the input alphabet, and delta is the transition function. Q0 is the initial state, B is the blank symbol, and F is the set of final states. Details. There are 3 levels of details we might use to describe the Turing machines. First one, we have to give the complete formal description and the implementation description, and finally high-level description. Comparison with the previous automata. The following table shows a comparison of how a Turing machine differs from a finite automata and a push-down automata. Finite automata doesn't use stacked data structure, and whereas push-down automata uses the last in first out, and finally Turing machine uses the infinite tape. Finite automata and Turing machines are deterministic, and push-down automata is non-deterministic. If there are more than one comparison, then push-down automata fails in that case. These are the comparisons. Relations. This figure depicts the relation between finite automata, push-down automata, and Turing machine. If you observe the figure, we can find the relation between these 3. Time and space complexity of a Turing machine. For a Turing machine, the time complexity refers to the measure of the number of times the tape moves when the machine is initialized for some input symbols, and the space complexity is the number of cells of the tape written. Time complexity of all reasonable functions is O of n log n, whereas space complexity is O of n. Accepted language and decided language. A Turing machine accepts a language if it enters into a final state for any input string W. A language is recursively enumerable generated by type 0 grammar if it is accepted by a Turing machine. A Turing machine decides a language if it accepts it and enters into a rejecting state for any input not in the language. A language is recursive if it is decided by a Turing machine. There may be some cases where a Turing machine doesn't stop. Such Turing machine accepts the language but it doesn't decide it. Types. There are total 11 types of Turing machines present. I will discuss each and every one briefly. First one, multiple tape Turing machines. These have multiple tapes where each tape is accessed by the different heads that moves independently of the other heads. Second one, multi-head Turing machines. These have a single tape with n number of heads where each reading symbol on the same tape. Third one, multi-track Turing machines. This Turing machine has a multiple tracks but a single tape head that reads and writes off all the tracks. Fourth one, semi-infinite Turing machines. Such machines have left ends limited by an end marker and infinite right end. Fifth one, universal Turing machines. This is a type of Turing machine that simulates an arbitrary Turing machine on an arbitrary input. Sixth one, alternating Turing machine. This is a non-deterministic Turing machine that accepts computation that generalize rules used in the definition of complexity classes of NP and co-NP. Seventh one, non-deterministic Turing machine. In such Turing machines, for each and every state and every symbol, there exists a group of actions that the machine can have. Eighth one, unambiguous Turing machine. This is a special type of non-deterministic Turing machine where for each input there is an exactly a single possible computation. In many ways, it is similar to a deterministic Turing machine. Ninth one, quantum Turing machine. It is also referred to as an universal quantum computer. It is an abstract machine that models the effects of a quantum computer by providing a simple model that covers the power of quantum computation. Tenth one, read-only Turing machine. This is a class of model of computability that behaves like a standard Turing machine and moves in both directions across a given input, except it cannot write to the input tape and only reads it. Last one, probabilistic Turing machine. This is a Turing machine that is modified to execute randomized computations. These machines make decisions based on the outcomes of the unbiased coin tosses. These are all the types of Turing machines which we can have in the present. Applications. Different types of Turing machines find applications in different areas of computer science. These includes complexity studies, software testing, evolutionary computations, software engineering, computer networks, machine learning, and finally high performance computation. These are the applications of Turing machine in our current life.
Understand Turing machine better by these following examples. Here we are given to design the Turing machine for the string a power and b power and where n should be greater than or equals to 1. If we are given like this, that means we're going to have equal number of a's and equal number of b's followed by the blank states on both ends. So the demonstration I will explain in the simple way. When we are given the strings like this, we have to go to the initial string and mark it as x or 1 or something, whatever you want. And after marking it, we have to move towards the right until we're gonna find the new string. We have to keep moving towards right, and after finding it, we have to mark it as y, as we found b here. Okay, after marking it as, we have to traverse to the left like this, and after going to the initial loop, so we're gonna like ignore the x as it is already marked with x by a, and we're gonna move towards right. As we found a, we're gonna mark it as x, and we're gonna finally move towards here. As we already marked here, we're gonna again ignore it and move towards the final one, and we're gonna mark it as y. In this way, we're gonna mark all each and every elements and finally reach the blank state. So when it reaching the final state, it will be halted and will be accepted by the Turing machine. Let's design the finite automata for this given example. Let's take a couple of blank states and followed by a and b. Okay, so here let's take the finite control should be there, and the read or write head will be there. Like it can move in any direction, like both right and left, whereas it would be only move towards unidirection, that is only it moves towards right for the finite automata and push down automata. And the length of the tape is infinity, and we can both read or write. So let's design the Turing machine for this one. Initial state will be taken as q0, and as we found the the initial string, we're gonna mark it as x, that is a. We're gonna mark it x, and we're gonna move towards the state q1. We're gonna simply move towards the right, and after finding the string b, we have to mark it as b. We're gonna mark it as y. Okay, so we're gonna move towards left, as there were only two strings were there. Understood? After reaching the final string, we have to traverse back again. So in the meantime, intermediate actions would be also performed, that is a. As we are ignoring them, we're gonna write the state wasn't changing, so we weren't marking anything, so simply write AAR as we are moving towards right. And after moving here, we are moving towards left, right? So here the states we weren't changing anything, so simply write AAL as we are moving towards left towards the initial state. Okay, after the reaching the initial state, we got x here. So we no need to change the mark. So simply write x x r. If you're gonna find x, simply ignore it and move towards the right. Okay. Now see, we have reached here and we found the a. We have to mark it as x. So we marked it as x, and we are moving like we ignored the a, so we ignore the a and move towards right. And we found the b, like here the y is there. So we have to do something regarding this. In order to ignore, you have to write simply y as we are ignoring this and we are not changing to anything. We are simply moving towards right. Okay, so we are moving towards this string, and you can see like b gonna change to y. It changed to y, and again it was moving to the left. Okay, and here it was moving to the left means y is there, so we have to ignore it, right? So I have to simply write y in order to move towards the initial string. Okay, and it reached here where it gonna reaches the a, like the initial string a. So after reaching the initial string xxr, we're gonna again traverse back to the initial state and like run the loop. That is a, like the x were ignored and the a had to change to x. So we had changed the a to x, and we have to like no, we have to ignore the number of a's and y's which were there in the way. We are gonna reach the final b which were there. We have to change it to y. We change it to y, and we're gonna again traverse the loop. You can observe that each and every state was filled, so that means that like we reached the almost final state. So we reached the blank state here. Okay, so that is q3. As we reach the y's were there, we have to simply move towards right no matter what. Okay, after moving towards blank state, we can observe like how many number of y's will be there. We have to keep on moving. If you're gonna change to y, you have to keep on moving towards right. So after moving towards right, as you can observe, we reach the final state, that is the blank state. In this way we can understand that the like after reaching the final state, the string gonna be halted and would be accepted by the Turing machine. This is how the Turing machine works. Example, here we are given to design the Turing machine for the string a per n, b per n, c per n. So like we said in the previous example, let's take blank states and consider equal number of a's, equal number of b's, and equal number of c's. Okay, so the initial string would be marked as x, and it's gonna move towards the second string, it will be marked as y, and it moves towards the third string would be marked as z. So after moving, like it will be reaching to the like initial state. Okay, after reaching the initial state, it gonna ignore this and mark the remaining ones as the x, and ignore this and marked as y, and gonna ignore this and mark this as z. After marking all this, like it gonna accept by the Turing machine, and the string will be work. Okay, let's design the Turing machine for this one. Couple of blank states, and a followed by b c. Okay, so reader write finite control. Okay, so let's take the initial state as q0 and mark it as x. So simply ax, oh actually we're gonna mark it as x, so we're gonna move towards right and mark it as y. That is q1 state, b gonna move towards right, as we are having three strings, right? Okay, so after reaching here, it's gonna move further towards c, which is the final string. It's gonna mark towards as z. As we reach the final string, we have to traverse back, so it's gonna move towards the left. So in the meantime, like intermediate operations would be performed, where we're gonna ignore the a. We're gonna consider the first string only. So as we marked it already as x, we're gonna simply ignore it and move towards right. Also similar to here, b as we already marked b as y, we're gonna simply move towards the right. So after moving towards here, so the we are right now at this state, we have to move towards the left, right? So we have to ignore the z and move towards left. That means self would be there where z z l. That means we have to ignore the z and move towards the, okay. And we can see like many b's and a's would be there. Well, we can even ignore them. That is maybe left, and y also there, so y, and even a also there, so simply ignore them, okay. And it's gonna reach to the initial state, and even x was also there, we're gonna ignore the x also, okay. So now do it for the remaining ones. A, where it will be marked as x, and the a gonna be ignored, and b gonna be, so here y is also there, so simply we have to ignore them. So simply write y r, right? As we ignore them, simply we're gonna like y by r. It wasn't changing to anyone. So here b was there, which will be changed to y. So simply mark it as y. And after that, b was there, like ignore them, move towards right. Z was here, and we have to ignore them and move towards left. Like as we found the c here, uh, like we have to again traverse back. We have to find a, and we have to find a gonna be marked as, yeah, like after reaching here y. So after finding the z, we have to move towards right, as we have to even mark for the c. So here after reaching q2, we have to move towards z, right? Okay, we're gonna mark it as z, okay. After marking it, we're gonna simply ignore it and move towards the initial state, that is x. We're gonna like ignore the x r. We're gonna simply move towards here, and when we're gonna find a, we have to mark it as x, and we're gonna move towards the b. So like as we found the y, we're gonna simply ignore them, and finally we're gonna move towards this b, and we're gonna mark it as y, and we're gonna move towards right. And after finding z, we're gonna ignore them, and finally if we're gonna find the c, we're gonna mark it as z. In this way, like we marked each and every string right from the a to c. You can see like each and every string was marked. So after reaching z, like what we're gonna do, we're gonna again traverse back, right? We're gonna move towards y, okay. So here we have to say, like after moving towards x, we're gonna move towards right, that initial state. After going to the initial state, as each and everything was filled, we're gonna traverse to the y. So here, as we filled all of the state, we have to go to the final state, that is y by r, which will be go to the q3. Sorry, my bad, that is q4. Okay, we're gonna move towards right. So after like we're gonna move towards right, we have to ignore each and everything which were like each and every y which were there in this. So even like we're gonna move towards z, so even we have to consider z also. If we're gonna get z, we have to keep on moving towards right. So after that, we're gonna reach the final state, like that is the blank state. So after reaching the blank state, you can move in any direction you want, okay. This would be the final state q5, okay. So in this way the Turing machine works. If you're going to take any example, like for example a b c, okay. Let's take a, it's gonna go to a, it be marked as x, and it's gonna move towards b, it will be marked as y, it's gonna move towards z, it's gonna mark like it's gonna traverse back to y, it gonna ignores them, and it gonna move towards a and ignores them, and it go to the initial state, and after that it gonna march towards x, okay. After marking like a to x, you can observe that it gonna move towards b, that is like it gonna move like ignore the y and go towards. You can observe here we don't find the b's, enough b's here, okay. So it would be in the trapped state, like these kind of strings won't work, okay. These kind of strings would be failed in in this case. So in this way, in order to accept the Turing machine, like each and every string has to be finalized in order to accept by the Turing machine. That's it for the that's it from my side, guys. Sorry for the bad writing.
That's it for the video, guys. Thanks for listening to me, and I hope you got better answers regarding Turing Machine. Thank you.